Thank you so much. It is my pleasure to start our panel. And I would like to introduce the members. But first, I'd like to tell you why we're holding this panel. The idea, of course, is that we are facing digital transformation across many domains. And even in domains that have been crucial in the past, now you have to view them from a new lens. So today, we'll be talking about the digital transformation and AI for energy security. I'm pleased to introduce the three panelists. Professor Changhyun Hsu, if you want to come up. She's an assistant professor of electrical power and energy systems at KTH Royal Institute of Technology. She works on control, optimization, and stability and reliability of the microgrids and vehicular power systems. She studied at Tianjin University. She got her graduate studies at Nanyang Tech University in Singapore. And she has a large number of awards and recognitions, too many to list that early in her career. Thank you for being here. I would like to introduce Professor Sarvmesh Bose. He's an assistant professor at Electrical Computer Engineering at UIUC in power and energy systems. He works to enable the integration of renewable and distributed energy resources. He did his undergraduate studies at IIT Kanpur and graduate degrees both from Caltech. Good to have you here, Sarvmesh. And I would like to introduce also Professor Lars Nordström, also from KTH Royal Institute of Technology. He's a professor of information systems for power systems control. He's the head of the power and energy systems, deputy head of the Department of ENCS at KTH. He works on architecture, functionality, and quality of information and communication systems for power control, operation, automation, and protection. Myself, I'm Kostas Panos, professor of ECS at UC Berkeley, and very honored to be able to introduce and moderate this panel. So I would like to start by asking each one of the panelists to address the fundamental question. Energy security is crucial. How is it being transformed by big data, IoT, AI, and related tools? Each one of you, maybe you can take a few minutes to expand on that, maybe using examples from your own work. And then we can go on with additional questions. So maybe?
Yes.
Start? Yeah.
Yes, thank you, Kostas, for this nice introduction. For the starting question about energy security and how AI and digital transformation can make the solution for the challenges, I'd like to share my project as an example. My project, funded by the C3IDTI, is about voltage security challenge caused by the high penetration of renewables, and we use AI and digitalization to address this challenge. As we know, power grid are moving towards the high penetration of renewables and electric vehicles. As electric vehicles and renewables, they are highly uncertain and stochastic. This will cause this voltage fluctuation, which may lead to the security violation or even a system collapse. Therefore, today's grid cannot accommodate high penetration of renewables and electric vehicles. On the other hand, the power electronic converters, which are the interface of these renewables and the electric vehicles, they have the full controllability and the flexibility that are possible to be utilized to address this challenge. But to control these power converters, however, as mentioned, the power grid are highly uncertain and volatile, that the accurate power grid model is difficult to be obtained. And second, we have hundreds, thousands of converters in the power grid, and to coordinate them, it requires high communication burden. Therefore, our belief is that AI and digitalization can play an important role to address this challenge by making the converters more intelligent and to stabilize this complex and changing grid. So our objective is to leverage this ongoing digitalization of power grid and deep reinforcement learning to develop communication-efficient coordination of converters. We know deep reinforcement learning is about intelligent agents interact and learn to make optimal decisions in the uncertain environment from data and experience. So we have developed a optimal control policy on the advanced simulation environment, incorporating dynamics of power converters using deep reinforcement learning. And then, considering the high communication burden to coordinate hundreds of thousands of converters, we further developed a decentralized deep reinforcement learning for practical deployment in large-scale grid. And the final result is that we achieve the local converters to interact with learn to interact with the environment, with the uncertain grid environment, and achieve smooth integration of renewables without the voltage violation. So this is our example about how deep learning, a deep neural network, how the deep reinforcement learning, how the digitalization and the AI can be used to address the energy security challenge. And of course, energy security challenge, there are also other issues like cyber attacks, natural disasters. So yeah, other panelists, comments?
Thank you. Lars?
Yeah, I agree very much with what Qianwen is saying. I mean, this fundamental change of the power system from an old, inertia, slow system, a bit like me, to young, much more dynamic systems by power electronics. That's really a big change, and how we can manage that, I'm sure that AI and data is a big factor. I want to bring in a slightly different perspective on the same note, though. I mean, when I started out in this business, security came through obscurity. Nobody really knew what the power system was about. There was a big centralized thing. A few engineers knew what it was all about, but nobody really cared. And with the change now that we're seeing this transformation of the system around us, EVs, PVs on rooftops, and everyone, smart meters, younger people that see the system changing, they also want to access the data for their smart meter. They want to optimize the charging of their EV. So there's this openness, or the grid is opening up at the edges to people that want to use this data. They don't want to be relying on a centralized, super clever engineer that has optimized their energy usage. And I think this is also a fundamental change that happens sort of around the system, that people, the average user, from the small residential person to the business user, expects to be interacting much more with the energy system from let's call it data or cyber perspective, which then in turn pushes the older engineers to be like, okay, yeah, we need to open up our data. We need to be aware that people will be asking us questions that we weren't used to earlier. And in a way I mean, perhaps a bit too naive, but some sort of energy community might be opening up in that sense, where we're all helping each other to optimize and control in that sense. And I think this openness is not something which is traditionally electric power engineering. It's much more a data science and computer science aspect. And I think that's also a big transformation that's happening on the people end of this.
Very good. That touches on some of the subsequent questions. But before I go to that, I would like to hear from Subhamas.
So if you think about sort of energy security, I mean, it is affordable access to uninterrupted electric supply. That's the definition I found on the web, right? So, so what can cause disruptions? Can be intentional or completely incidental. Incidental, how can that happen? Well, natural disasters, or mainly the disasters that happen or that interrupts electric supply, they happen due to the fact that we did not anticipate or plan for them, right? Now, you cannot plan for everything. If you have to weatherize everything for minus 50 degrees Celsius weather, at minus 50 Celsius and Fahrenheit doesn't differ much. So at that kind of temperatures and everywhere in the grid, that's perhaps being too conservative, right? So perhaps some kind of risk-sensitive planning and so on and so forth one can think about, right? But in this, think about as future rolls out, you're going to have things that we don't know yet. For example, EV load patterns. We don't know how it's going to look like. How people are going to driving patterns will impose loads on the grid. We don't know. We don't have data. Without data, we can't really think about how to plan for them. And so this data generation needs some synthetic models that perhaps those models that we create based on what we think it might be, that synthetic data creation should then accommodate new data as coming in and refine those with data. So that's both a challenge and an opportunity, right? So this is the incidental part, right? And then there is the issue, which is sort of the interruptions that can happen due to the intentional part or due to the malintent of somebody. Now, in that, you can attack the large or the small, right? The large would be, let's try to attack the control system of a particular generator, right? Now, I don't have any much insight to offer into sort of computer security and securing that, but that's an important problem. One needs to secure a big generator. If you can trip a nuclear power plant out, that can cause a problem, right? So there are challenges associated with that. But then, as the grid is transforming from this top-down centralized architecture to something distributed, right? So we have multiple small actors, as Lars was saying, right? So now think about what an adversary could do. If I attack one distributed energy resource, that's a toaster to the grid. It doesn't matter, right? But it does expose you to something that we did not think about. That is, if the industrial control systems get homogenized, then a malware update can basically make thousands to possibly millions of distributed energy resources that are attached via converters to malfunction. That's an attack at a scale that we would not have anticipated. Here, the culprit is the homogenization of the technology. So if you can make it diverse, somehow you can get rid of it. Now, this one controller at one distributed energy resource would not be able to detect anything, right? Because it can pass muster there, but at a global level, this is creating some kind of a problem. So you require fast detection mechanisms and so on. Now, it is kind of, whenever you try to detect these kinds of things, or you want to do distributed computation and make it private, that's what my project is all about. One of the challenges is you either have to believe the data and then sort of say, well, detecting changes in the grid, changes in the model, and so on, or you have to believe the model and then say, well, the data that is acting funny is due to some malintent. So this two things that Amritanshu's presentation mentioned about. Is it incidental or is it intentional? It's not often easy to detect. Perhaps the only way to go about it is what Jawad talked about. There is an inherent randomness in the incidental one, but the intentional one may not have that. So with that, probably this opens up a lot of questions in terms of both presents us with challenges as well as opportunities. Thank you.
Thank you. So I would like to follow up on that and soon open it to the audience. But what I'm hearing is that, what I heard from all three of you is that the grid is, the power system is much more complex, much more diverse. So much so that you cannot control it with classical methods, right? So AI, machine learning, big data, black box approaches, are perhaps something that we should use. You mentioned, Lars, security through obscurity. Now we have a different kind of obscurity, right? The obscurity of complexity, which of course, but the data is transparent. So anybody, including bad actors, can benefit, can take advantage of that. You mentioned, Salman mentioned the inherent randomness, right? We don't know what is going on, and we don't know what the intention of people are going on. So I would like to go up and ask a little bit more specific questions. Now that we have so many players, both good and bad, let's focus on the good players. How do the responsibilities get distributed? I, as a homeowner, what responsibility do I have through my solar panel, power converters, inverters, and so on, my participant? I, as an electric vehicle owner, what is my, and so on and so forth, including the producers of these products. You want to take a stab at that and tell us about your opinion about how do the responsibilities fall out?
Yeah, so responsibility for this distributed energy resources.
For the safety of the
for the safety of distributed energy resources, Well, as first, as mentioned, this cybersecurity issue, like if the data is like corrupted by some bad actors, then it may result that it is not very traceable. But since these distributed energy resources, they are more kind of distributed, so not like a top-down control of power system. So with this, they can have this distributed operation. And so, like also, we want these distributed actors be a more active participant in the grid operation. So we, for example, this grid code are being updated that these distributed energy resources, they should be responsible to operate in grid support mode when there are some security or this stability issues. Then with this, for example, for my project, I have this converter in assets, distributed energy resources. They should support the grid voltage when there is this security issue. And my solution is decentralized solution without real-time communication. Then by this way, even when you have cyber attacks on the top, then because my communication will not be affected, I can my converters can automatically react to the grid situation and provide grid support. So I think that we can, like grid code can be updated, and also this decentralized or distributed solutions can be implemented so that they can provide active support even without like real-time communication or limited communication, so to guarantee, to enhance the resilience.
So resilience at the edge, right? I mean, you have all this, yeah. Great. So
yeah, I think I was just trying to find a metaphor for what we're talking about here, and it seems that, I mean, right now we have the fuse. If something bad happens in my house, the fuse blows. And now we would want to have some sort of cyber fuse then. Yeah, so that it would detect bad things going either way, whether it's electrical, digital, whether that could be the same, I guess, but never mind. So that comes back a bit to this, the grid codes. I mean, it's going to be some time till we see it at the residential level, but the European grid codes now have defined this significant grid user. And these significant grid users, which are up to now defined as generators or larger distribution grids, they need to follow these grid codes. And I guess what we might be seeing is, of course, some sort of gradual shrinking of the scope, what these grid codes could imply. And eventually we would have perhaps that cyber fuse, which if you are not helping, if you're actually hurting the system, you will be disconnected, both electric and cyber-wise, because we have built a distributed system and it's a shared one, but we have a common good that we want to upkeep. And I guess that's the cyber fuse, I guess.
Actually, the cyber fuse metaphor is quite interesting. You know, as an electrical engineer, many of us are, would know that fuses are fairly autonomous devices. They don't need to know what is happening in the big picture. They respond to a very localized signal. Do you envision something similar here?
Yeah, that was what I was thinking. But whether it's, I mean, starting out from just the electrical anomalies, that's easy for the fuse. But then having this anomaly detection already at the household level, I mean, that's stretching it a bit far. But I guess I would assume that if my router at home starts behaving differently, my ISP would disconnect me, and that's something that's happening at the other end too.
So I was also trying to search for a metaphor. So the way I think about this is that as kids growing up, right? Back in the day, consumers, you think about them as sort of, you can do whatever you want, but the grid would be completely tolerant to whatever you do because you're too small an actor, right? But the kids are growing up. We are, from consumers, we're basically becoming prosumers. And so at this moment, as kids grow up, they have to subscribe to a social code to live in society. So will building codes and grid codes evolve as a mechanism to do this. But not all problems stem from acting bad. It can also come from honest but curious adversary. So for example, if I just observe data, right, I may be able to say something about whatever, whether you are at home, whether what are your driving patterns, which restaurant do you go to, and those can be used for nefarious purposes. right? So these are honest but curious adversaries. So one must then also build on top of it computational capabilities that account for the presence of these kinds of actors. By that I mean, you basically have to somewhat add noise to the system in a meaningful way such that certain computations still give you the right answer, while some others don't. And so privacy becomes somewhat of a problem which cannot be tackled at the household level. This is somebody who's managing the data flow has to take care of.
Okay. Okay, so can envision then a grid where we have multiple cyber fuses. So an adversary will try to find perhaps the most vulnerable point at the edge, will be quickly isolated. But let's talk about adversaries now, bad actors. We have to assume that they're as intelligent as we are. They have the same tools, or even better, and they have access to the data that we have. What then? I mean, what now? Because that's the case, right? So how does it change? Does it change the game in any way, or is it an arms race?
This would be speculation, but I mean, there is a couple of still fundamental electrotechnical aspects of the grid that might very well keep it running. And if we, I mean, at the local, I mean, we need to have some, in that sense, if we could have the cyber fuse protected, so that if we were able to be containing us and have a resilience approach by establishing microgrids, but that would then in turn require that we had some sort of islanded mode and be able to control. But then if you put the adversary inside of that, then, I mean, it all breaks down in the end. But the cyber fuse would be something that, in this metaphor then again, being able then to also make sure that we do isolate us in that sense. But I mean, if they're just as smart as, well, if they're smart as me, that's not a problem at all. But if they're smart as the other guys, that's going to be a problem.
Shankar. Absolutely. We're about to open to the audience. Anybody, but if anybody from the panel wants to comment before you open up? Okay, Shankar, go ahead.
It's important that when we think about digital transformation, there's a society, it's not just a technical problem. There's a question of pricing. There's a question of responses to pricing. And some of the things that Subhamesh just talked about, what you can glean from smart meter data. I don't know if Zico's in this room, Zico Coulter and others have had lots of, there's a lot of literature on this. But my question is really, if pricing is a way to start thinking about quality of service, how come it is that mechanism design for the utility, whether it is to include renewables or not, has been a total disaster? In the state of California, it was a disaster. Last year in Texas, it was even worse. And so the question is, maybe pricing is needed, and maybe that would include this question of islanding if you're under attack and working through attacks. But what is the take about bringing pricing? What I heard so far from the panel was exclusively the technical and not the economics. But societal systems have real money, and there are real other considerations. So what is your take on how you'd bring those in?
I can give a sort of take a stab at it. So the question of pricing, the way I understand it, again, let's go back to the kid metaphor. It helps to think about this. You sort of develop this give and take relationship with the kid, right? How they behave, and based on how they behave, you put carrot or a stick, right? Now, this kind of a mechanism works when the actor and you have basically common goals. But so pricing, the way I think about it, is the mechanism to continuously provide the power, get it from whether the prosumers, and build a mechanism for them to be able to participate in the whole energy economy, not just as side actors. Currently, we're thinking about all the distributed energy resources the way provides a little bit of frequency regulation, little bit of reserves, but still the power grid's main stuff is still the action is in the transmission grid. That's where all the core power system still lies, right? But we are trying to decentralize it to the maximum extent possible through mechanisms there. But when that fundamental assumption breaks, you don't have the same goal. That, I don't know whether the pricing is the right mechanism at that juncture. If you still have somewhat adjacent goals, then pricing is a mechanism to perhaps form a central, form a coalition of ideas.
Yeah.
I really didn't get the difference between pricing, transmission, and distribution. Why not price them both?
No, you can. You certainly can.
I mean, I don't understand your objection, really.
No.
Because you could, if there is a grid, the grid could be at the transmission level, you price it there too. The problem seems to be the mechanism itself is flawed.
Right, right.
The mechanism is flawed because, in a capitalist society, I understand there's some that are not, but, in a capitalist society, that's, I don't know what other lever you have to be able to, you can't differentiate electrons. They're all the same.
Right.
But on the other hand, you can differentiate the service.
Mm-hmm.
And I mentioned this work of Coulter, and we've also worked on this. I mean, this question about privacy settings. What Zico and others proved was that if you have a sufficiently high frequency readout of smart meter readings, you can determine what appliances are being used in a given household. That's pretty invasive. It might be great for demand response, but not so good for privacy. But on the other hand, you can provide a scheme whereby you say, I will only read out at 15-minute intervals, which is too low frequency to be able to do this, what's called disaggregation. That's what this thing is called, of the usage. And then the questions also about the social good versus the good of the individuals. That's all. Professor Burge was asking some questions here. He's an expert in actually trying to understand the gap between the Nash equilibrium of individual people trying to maximize this and the good of the society as a whole. But nobody is trying to do this at the grid level.
So just to quick follow up on this, that I completely agree with you. I mean, the pricing, the right design at the distribution level needs to be figured out, and bringing it within the sort of the realm of the whole transmission wholesale market mechanism, that needs to be figured out. No doubt about that. But where I'm sort of I don't know whether it's the right approach to think about when there are adversarial actions, where their motivation is not actually to get the maximum profit or any of that sort. Their sole goal is to break the system. There, whether it's the pricing will work or not, I'm not so certain.
Actually, pricing is of course important to involve these participants for the market. But also, now we have this digitalization, this AI technology. We have huge amount of data. Then with this, we can learn a lot of new strategies to improve the current pricing mechanism, current market mechanism, and considering new solutions. As you mentioned, there are maybe some adversarial, like privacy issues. But with this big data learning from this, we get more improved strategies, like for extreme situations with current pricing mechanism. Of course, the system cannot work, but with the digitalization, with the new technologies, this solution, advanced pricing suggestion market mechanism, it can work in the future.
Just a couple of thoughts, to add to that. Shankar, pricing has worked beautifully at the supply level and not so beautifully in the past during the Enron days at the supply level. It has not worked very well at the distribution level because for pricing, by the way, I do not view pricing as an economic issue. It's part of the technology that controls the grid, right? It's a controller essentially. It's not divorced from that.
Yeah.
But the reason it hasn't worked at the distribution level is because it's hamstrung by regulations. And it is at a level that this pricing model, this market has quite a bit of friction right now. And because you're talking about small values at the prosumer level, any friction is going to kill it. Okay? But there is quite a bit of potential to unleash that and have a better control. And of course, there's going to be a source of vulnerabilities too, because people will try to game the system. So, so by the time we design those mechanisms, we have to make them robust to bad actors. Certainly a field of glory for many of us, right? If you want to work in this area. I think there's quite a bit of potential there.
And if I can add, there's also this challenge that if you do put a mechanism in place at the lower residential consumer end, tariffs or subsidies or something for PV or EV, people invest and they start to benefit from that model. And then to set in place the mechanisms for the greater good is much more challenging because it involves many more actors. And then you have the lower level mechanisms that people are optimizing with. And then you want to bring in, okay, couldn't you also provide reactive power or something? And then they're like, oh, that breaks the nice local optimization. And that could also problematize it.
But are these insuperable? The issues that you say, are they impossible to solve?
They're not impossible to solve, I would believe, from an academic standpoint, but getting the policies in place in time, since the local business is much faster to move to some sort of subsidy or tariff, while the greater good takes a lot of policy making, and then you already,
Yeah, like currently the grid code is being updated that those distributed energy resources, when the grid has some emergency situation, they must be responsible to provide like frequency support, voltage support, these issues, or not only optimize their own benefit. So yeah, so this needed to be.
Yeah, so I have a question on the use of AI to design algorithms for a dynamical system like a power grid. Much of the successes of AI are in static data. I mean, like, how to distinguish between different faces, or can you tell if it's a cat or a dog or so on. Reinforcement learning, for example, fundamentally uses data to learn what to do. But when you deploy an algorithm that's designed using reinforcement learning, the system may not, the probabilistic description of the system or the deterministic description of the system may not be the same at the time when the data was collected to train the algorithm. So how do you incorporate robustness in I would think for a cyber-physical system like power systems, robustness is very important. And so you don't want to learn to do very well under some particular situation. For example, I work with the electric car company to design a automatic merging algorithm from a ramp onto a highway. Now, it's a very difficult question. Should you design the algorithm for peak traffic or moderate traffic or light traffic? Because if you design it for one, it doesn't work as well for the others. So we had to do a lot of additional ideas from control theory, like model predictive control or other things. So I was just wondering what, in the context of power grid, I mean, training something and learning to do something based on the current data may not be the most robust thing to do. And so what things you would, what are the things that you would do to make sure that at deployment time that your algorithms work well?
Yes, thank you. This is very important. When we do this research about deep reinforcement learning for power system, we notice that a lot of works, they use this static linear power system model that they do not incorporate the dynamics of power electronics. And this will, of course, damage this direct application in the real-world systems. So for our work, we develop advanced simulation model that incorporate the dynamics of power converters. So we develop, because we get data, so we first train this data-driven modeling for the converter, then we get the whole system. Then based on that system model, we can extract the stability region for each converter, and or we incorporate this in the deep reinforcement algorithm that you add one layer is about power electronic stability constraint for each converter, so that their reaction is within the stability region. And also, since our objective is to guarantee the voltage security, for example, in our project, so we add another constraint, another projection layer to guarantee the converter operation is within to guarantee the power system voltage constraint. So based on this physics, so like AI or deep reinforcement learning, the application in power system is not direct utilize this. We need to incorporate the physics of power system and maybe like incorporate the optimization and the control algorithm. Like our example is to incorporate 2 projection layers to guarantee all this is within the physical constraints. Then with this advanced simulation environment, we train the policies, and then we adapt to the real environment because we can guarantee all these constraints not violated. And with the real-time data, we can further update to do the fine-tuning for our model, so it can perform very well. Yeah, so this is our experience about deep reinforcement learning application in this power system.
I can add a couple of things so there are 2 issues here in sort of applying classic RL style techniques that I see in power. One is there is, at the transmission network level, the model is fairly good. And so throwing it out of the window and just trying to do something from data may not be the right idea, right? Where models may not work is where, for example, the models for our distribution grids, the way we lump them in the transmission network stability studies, those may be up for some data-driven learning. So model and data needs to somewhat come in together when in power. And the second one is more about the issue of non-stationarity that you talked about. Non-stationarity essentially means that whatever environment you learned in, it must change as your controller and the policies must change based on how the grid conditions change. Now, non-stationarity, there's a lot of work coming out now in non-stationary RL. I myself have been trying to do some in that direction as well, or even detecting a mode change. When has a mode changed? Can you detect it quickly? I mean, yes, we can always think about this as hidden Markov models and run sort of POM-DP learning. It takes time. These things are time-consuming algorithms. Can you do it something quick and dirty, and how well will the quick and dirty work in comparison to the provably optimal? That is something that we are trying to even think about. So, but non-stationarity is something that one needs to work on. But if possible, incorporating model information in the power grid. Yeah. So rather than throw the model away and just rely on data, that's probably not the right way to think about it.
Good. Alberto.
Yeah, I have a couple of points. So one is about the modeling issue, right? So the fact that you need to mix physical models with some data-driven was well known. I mean, Costas may remember in his young age, SPICE 2 was based on the physical model, and then we added to it what we call the fudge model.
We call them macro models, but that's not.
No, we call it, the guys who develop it, we call it fudge model. And the fudge model was supposed to take into account second-order effects, that you didn't want to go into nitty-gritty details because it, being a second order, didn't violently modify the behavior, but you need it for added accuracy. And then we were fitting data like crazy. There was an HP equipment piece that was running overnights and running tons of characterization of devices. And then this data was automatically used with least square estimation, all of that, to determine the fudge factor. So I completely agree with you that going only on the data-driven model doesn't make any sense for me. So data-driven is useful where you don't know or it is too complex to know, call it, right? But if we know something, why throw it away? I mean, it's completely crazy. And this, I think, is also something that we as, we have many professors here. Guys, tell your students that ML is not the solution to the world's problem. Right? So I have this thing, I don't know what to do. Okay, ML. I had this issue now with a student. We are working on a very interesting problem, right? On designing an underwater device, right? And so they say, oh, we use ML to determine the model of this thing. And I say, well, it is a mechanical system, right? So what are the parts? how it's put together. This guy didn't even know how to write the equations for a model. I mean, that's what we are doing to our students. This is wrong. I mean, we have to teach students not only the power of the technology, but the limitation. And if you have got something that you know better, why throw it away?
Thank you, Alberto.
Well, okay, this on the side. So my strong recommendation is that try to figure out where ML works, right? And which is an approximation technique. When we come to physical problem, it's approximating, you know? And so there is books and encyclopedia about approximation techniques back from my other time. So are our students learning this, right? I don't know if they do. Now, second point is related to coming back to the energy security, right? We heard about the responsibility of the user, but I think the responsibilities of the device makers. I mean, if we look at one of the weakest points of the whole new technology is about the IoT devices. IoT devices are so miserably performing on the security that is amazing that we didn't have major disaster as yet. We had some disaster, like the light that were used to create a denial of service attack a few years ago. And lights, I mean, lights that have a microprocessor inside, the modern lights. So the point is, I believe that we have also to have the producer of the low-level device come into the picture. And in power, same thing, right? So if we think about how you get into the home, it's probably thermostat, right? I don't think, or other control devices on your washing machine or things of that sort. So why don't we hold responsible for increased security the guys who are making these devices? Then, of course, it's our responsibility not using a password 12345, right? And that is the password aspect, right? But I think that the first line of defense is just to get the producer of IoT devices and power system controllers to do more, right? And to make sure that they do not depend on the user, because the user is a turkey, right? I'm including me. When it comes to my home, I'm a total turkey. I don't want to think about 200 passwords, right? So the point is that we cannot depend on the user to make the energy infrastructure strong from security point of view.
Thank you, Alberto. And since we are on time, that is going to be an excellent subject to discuss over lunch. And I would like to thank the participants. And I would like to thank the audience for the questions. Thank you.
Thank you.
Thank you.